little bit recall last time. So we studied the differential manifold. So 有形。So anyway, and then 一个例子是球面。So Sn, which is the inside. Like this, define it. And then, so this is the set, and then you have the overflow, and then we define the U plus Sn minus source flow, U minus source flow. And then we define the through graphic projection by just connecting this south pole to the point here and then project to here. That's what we do. So this map is just given by 5 plus. Okay, 5 minus is the opposite. You just have like this way. Minus. So this is plus, and then here. So that's what we did. So as you can easily see, so this is U0, so this is the U0 point. So yeah. And then U0 and U minus 1. So therefore, as you approach to the U0, so as you approach to U0 is equal to minus 1, this becomes very small. Okay? So therefore, it just scales to the very far away. That's right. So therefore, often people write down Sm, it's just write down Rm and the input. Okay. And then so this is called stereographic projection. It's the graphic projection, and then what we did is that so we have a transition map from one to the other. So we have a transition map to the other. Just like this. This is function. That's one. Okay. Any questions at the moment? Okay. So that's what we learned last time. So okay, and then so later, in the homework you need to learn something like a RPN. So projective space. So projective space is the Sn, but you just identify the equivalence class, but the equivalence class X is minus X, okay, inside of Sn. Okay. So therefore, what you need to do is that so here, so you identify this point X and the opposite point minus X, like this one. Like this one. Minus X. So you just identify. Okay. So you just identify it, and then you just have a quotient space. Quotient space. Is quotient space for R. And sometimes people just consider it like this way. You just consider this space, okay? And then in the mod, the equivalence class is the X is lambda X, where lambda is the R. People just like that. So this means that you just consider the Rn minus 1 plus Rn plus 1 out to the Rn plus 1 and get rid of origin. Get rid of origin. And then, so you just consider the line along this X. Like this one. And then you just scale whatever. So the point is scale, so you just get rid of origin. And then you just consider the line and just quotient by any scaling from the infinity to minus infinity. So you just identify all the points along this line. That is RPN. If you do that, northern hemisphere and the southern hemisphere is identified, except this equator. So northern hemisphere and the southern hemisphere is identified. So this point is identified this point is identified this point, and so on. Okay. So therefore, for RPN, you don't need to consider the southern hemisphere, in fact. And then if you consider this equator, so equator is the Sn minus 1. Okay. But you have to identify the opposite point. So this point is identified this point, like this way, and so on. Therefore, what you end up with so this point is identified this point. But in fact, this point is not the point. N minus 2 dimensional map. N minus 2 dimensional map. So this N point, in fact, so this yellow line is R P N minus 1. You understand what I mean? Because I mean, so this equation is Sn minus 1. And then identify the opposite point, right? And also, this yellow line is Rpn minus 1. Rpn is include Rp n minus 1 as that so submanifold. Submanifold. That's what I'm going to say. So as you can easily see, so if you look at all the northern hemisphere and except this equator, so this is in fact can be identified with the Rn. Okay. So this the upper hemisphere, so the upper hemisphere is northern hemisphere, northern hemisphere is can be identified the open list, right? By different open. By 1-to-1 map, you can just project to this Rn. It's just you can map 1-to-1 by the open list, and the open list can be scaled to Rn. So therefore, topologically, so upper hemisphere is Rn, and then if you look at the same thing, but what's left is Rpn, right? Rpn minus 1. Okay? Rpn minus 1 also has the equal n minus 1, okay? Rn minus 1. And then at the boundary you have Rpn minus 2. So therefore, you have the Rn minus 2 and so on. Like this. So that's how it looks like. So RPN projective space is just that you have a big flat space topologically, but at the infinity you have the another plane. At the infinity you have another plane, and then if you go to this plane again at the infinity, you have another plane, Rn minus 2, and so on. That's what's really the solid composition of the RPN projective space. Okay. Any question at this moment? So submanifold. Zubioshi is the as I mentioned. So one of the examples is here. Okay. So we have M. You have an M prime. Okay. And then you have the open patch. So if you have a manifold, so as I mentioned, the manifold is an open covering. Open covering. And if you look at the here U1, and there's a map to the coordinate like this one. Rn minus 1. Rn minus 1. And then, so So some manifold is that the one of the coordinates can be 0. So here we have, so this part because is mapped to like this. So this part is mapped to. So therefore, so M prime of U is that the Q inside of U is the X plus 1 Q is 0 and so on. So this, in this case, M prime is called M prime dimensional submanifold. Submanifold. 表示很前卫。And then, so so transverse direction. So this transverse direction is the n minus n prime codimension. It's called codimension. Okay. That's how it is. For example, 例子，一个例子是，那你给我一个例子，300个，请给我一个例子，300。The simplest example， 最简单的例子是 R n prime 1 R n。So of course n prime is less than n. So when you set x1, to be 0. This part is R10. That's the summary. Of course, another example is Sn prime, Sn. That's the equation. So you can just put the equation. That is also submanifold. Another example is if you consider Riemann 曲面，曲面，黎曼曲面，那这个哇 ，this is S1, become S1. This is also submanifold. Okay. As you can easily see, so if you just got the open covering like this way, open covering like this way. Or, because I mean, if you consider torus, these are literally submanifold. Like this one, yellow line. Those are S1. This one, like this. Those are also submanifold. So many Okay. Any question? So another thing is that so if you consider two smooth manifold, 光滑有形光滑，怎么写呢？ Yeah. Then you can consider so-called map, smooth map, which is called 光滑映射。 Smooth map. Smooth means you can differentiate infinitely many times. So if you consider the m here, m like this one, and then you have open covering. So this point is, suppose this point is mapped to this point. So P, so F of P. Okay. It's mapped like this. Suppose this U is mapped to F of U. Yeah, I think it's better. Sorry. Whichever is okay, actually. In fact, it's whichever is okay. F of P. And then you have another open. So here you have a B open covering, and it's mapped to psi, and it's mapped to like this one. Okay, we do the F, map F. Now we can do the following step. I think it's better to use the other color. Sorry, I think this. Okay. So smooth map is that the phi inverse, and U is mapped to here, and then, sorry, I think I made a mistake. Sorry. And this U is mapped to here by F, and the F of U can be something like this. Slightly different. Slightly different. So the alpha intersection is something like this one. Okay. Intersection. So this yellow part is mapped to F inverse, phi inverse mapped to this part, and this yellow is mapped to here, and the intersection between yellow and red is mapped to here. So therefore, so for yellow to this intersection, you can just have phi inverse F psi. Phi inverse F psi, you can map yellow part into here. Okay? Some of the yellow part. So this is Rn, open space to open set to open set in Rn. So therefore, you can have a notion of the differential. Wave. So therefore, if this is the smooth everywhere, so all the point you can have this kind of, you can just construct this kind of map. If this is smooth, this map is called 光滑射印. Okay. So 例子是So 例子是 as follows. For instance, S2. We can just have S2 plus S2. Maybe it's better to different. Okay, for example, so if you have a product manifold, the projection, you can have projection. This is P1. This is for projection. So these are, if you have a smooth manifold and product manifold, so product or smooth manifold, and if you just project to this, or for instance, if you have an X and a Y, you just set the X here. And then like this way, so you just have some point P, a fixed point P, Q point Y, you just project to them. Oh, sorry, but it's just Y. Just not X, then you have a smooth line. That's one of the simplest example. Another example is that the yeah. And then if this F has if F has an inverse plus inverse, then F is called diffeomorphism. Okay. Yes, smooth inverse. Yes, smooth inverse. So, for instance, yeah, I think this is called 同配. I think I search, yeah, 同配. Waveframe 同配. Waveframe 同配. Okay, so this Tongpei, Waveframe Tongpei is actually very, how to say, very interesting thing. It's very interesting. For instance, if you have R is this line, and the point X is mapped to x cubed. You can map like this. Yeah. You can just map like this. And then, so this one is this one will give you the different differential structure to R. Do you understand what I mean? Do you understand? X goes to x cubed will give you different differential structure from usual differential structure to the like a unusual differential structure from x to x cubed. So this is different. Okay, another example of differential is the S2. By rotation. By rotation. So this rotation of S2 is or Sn. So you can just have rotation in each axis. You just have rotate. If you have a rotation, x, y, z, like this way. So in this example, there's 2. You can rotate. That will just create so-called the generate so-called the group of different models. So group of different models. So if you have a different model, F is mapped to Sn, goes to Sn, okay? And G is mapped to Sn, goes to Sn, both different. So therefore composition also give you Sn. Okay? Composition. So first you just go to map to Sn, and G in Sn. Okay? Like this composition of different movement. So therefore you have this composition also give you different movement. So therefore, even if you multiply the map, you will get that another different movement. Okay. So therefore, you have a multiplication rule inside the different movement. So therefore, the homomorphism map will form a group. Because I mean, if you have multiplication, and identity is just an identity map. Okay. So and this group of homomorphism is called SON. In rotation group, this is in Chinese called rotational group. I cannot write down. Sorry. So in In other words, it just so if n, so it's an n by n matrix. N and n times x. Like this. Do you understand what I mean? So if that in Rn, oh sorry, it's not n by. Okay. So you have x, you have the normal is the length is 1, and if you rotate, even if you rotate somewhere, so this is ax. Even if you rotate, the length doesn't change. So for instance, yeah. So that's how you define this group. For instance, so this composition F and G just rotate like this way by Sayer, and you, rotate like this way, and you can rotate another way. That's F, and that can be G. Rotate and rotate. That is something like I will give you another rotation, like another rotation. So for instance, if you rotate, so for instance, x-axis and then y, like this way. Sorry, x and how can I? Let's use the big one. So if you rotate, for instance, this is the x, y, and z. Suppose if you rotate the x-axis, it becomes like this way. If you rotate y-axis, it becomes like this way. So you start with the rotate and rotate like this. That is equal to, yeah. And yeah, like this. So, how should I explain? Rotate. So yeah, it should be. So x, y. Yeah. Sorry, I got confused. Sorry, let me. How do you? So if this is x-axis, right? If you x-axis 180, and then y-axis 180. Y-axis 180 means like this way. No. Y-axis 180 means like this way. Okay. Y-axis 180 is like this way? Like this way? Yeah, like this way. Sorry. Z is like this way, right? Okay. But some composition is equal to z-axis rotation. I forgot. X rotation, Y rotation is equal to Z rotation. How? Is it pi rotation in total? No. Is it true? Is it true? So X in 180 and y in 180. But that is equal to z in 180. Something like that. It should be correct. It should be correct. Yeah. So, yeah. So that's that. Anyway, so that's is also different option. 配光滑流线的重配。Another example one can consider is so-called graph. So if you have f, this is smooth, and then we can just consider topology. Is the submanifold of this product manifold. So for instance, if you have M and N, and each point here can be mapped to N. Okay? For instance, like this point is mapped to this point. So N and each point of N is mapped to N. So this is N. Okay? So each point is mapped to like this way, and you can just construct by so-called graph. Gamma N. Okay? So this is the submanifold inside the submanifold inside a product manifold. So this product manifold is this rectangle, and then this purple one is so-called graph of the map N. Okay. Another thing is is the带边流行。So this manifold with boundary. Okay. Like this one. So boundary can be just mapped, considered as follows. So if you have the, so again, the manifold has an open chart, like this way. But at the boundary you have like this way. And if you just map to here, then it becomes like this way. So here, so this is N, and people open the boundary of N like this way, and then a point in boundary N is mapped to this point P, and by 5 is mapped to like this. therefore, phi of p of, for instance, xn is equal to 0. All the boundary is mapped to, all the boundary is mapped to this xn to be 0. Like this. That's easy. So boundary of n is also a manifold of n. Moreover, the boundary of n is also n minus 1 dimensional manifold itself. And then boundary manifold cannot have a boundary. What I meant is boundary of boundary should be 0. So for instance, disk, which is the x or n plus 1, and the norm is less than 1. So this the ball. Let me mention this. This is the manifold with boundary. Each you can have open chart like this way, and you can map this part to like this way. And the boundary of this disk is what? Boundary of this disk is what? Here. So boundary of this is Sn. Okay. Dimension. And then this Sn doesn't have a boundary. Okay. So boundary of a boundary is should be empty. So smooth man. So if it's empty, M is called closed man. So closed manifold is B Yoshi. B Yoshi. That's the case. Any question at this moment? So now we will consider them a bit more like a sophisticated concept. Sophisticated concept called tangent space. That's called Shit. Huh? Shit. This one, 진짜지? 공제, 실성 공제. Like this one? 실 공제. 실 공제. Oh, 他讲balance. Thank you. Thank you very much. 这个consent. Okay. Okay. Check consent. So check consent. The thing usually be at point each point P. The point P. You can just assign some vector space which satisfy the point. So find the vector xp. So P is a manifold. xp alpha f or psi. So is I should mention that the smooth map, the smooth map group of diffeomorphism, I call a C infinity of f. Sorry. So let's call C infinity of n is the space of the smooth map. This is smooth. So I define like this. So M to R, smooth map. I just write that C infinity. C infinity of n. So this tangent space is C. Smooth map is mapped to R. Like this. Okay, which satisfies the follows. Which satisfies the two conditions. So one is the linearity, which means that the xp. So this means that if you have a function over manifold, it's mapped to xp of f. Xp of f. So function is mapped to R. So this is R. Some element R. And suppose you have the two function, the given two function in manifold M, then the linear combination is also C infinity of M. So the alpha and beta is R. Alpha and beta is R. And then xp alpha f plus beta g. The linearity means that the alpha xp of f plus beta xp of xp of g. That's what I mentioned. So this xp of f is also f element of R. xp of g is the element of R, and you just multiply the element of R. Alpha and beta is just number. If you just multiply them, this is the inside. Okay. That's linearity, and then also here you have a Leibniz. And then Leibniz. So you have Fg is also C infinity of f. Fg is just a Fg of P is just Fp and Gp. that's okay. So you have a multiplication of the function on n, and you just apply the following thing. Like this. So this is called Leibniz rule. So this is called Leibniz rule. So they form vector space. So suppose you have a two vector space and yp, and then they and I call it this, the space of tangent space is called TPM. This is at point P, so the chip at point P. So then XP and YP is then alpha XP plus layer is also tangent space. But also, this is a vector space. So this satisfies it. So alpha xp f plus beta yp of f is also inside alpha. Alpha and beta is some number. They form vector space. So at each point you have a tangent space TPM. So for example, so another way to think of, so this is kind of an abstract way of consider the tangent space. But another way to consider the tangent space is just derivative of some curve. So for instance, if you have a manifold, if you have some curve inside a manifold like this way, and then take which is parameterized, the curve is just a gamma, which just marks the segment 0 to 1. Okay, sorry, -1 to 1. Like this one, gamma. And then we can just take a derivative at point 0. Like this one. Okay, so you can take a derivative like this. So Okay, so maybe, okay, sorry, maybe I think I should write down like this. And we're gamma 0. Then we can do the following thing. So if you have f, a gamma of t, and you can take a derivative. This can be understood xp x of f when t equals 0. So xp is literally the derivative with respect to t. You can take it like this. So for instance, and then let me write down. Okay, and then you have an open covering. Is mapped to like this. This Rn. So this is U, phi, and phi of U. And you have a curve on point P. You have a curve on point P. Like this way. And the point P is mapped, the curve is mapped like this. That can be also compared with something like another curve. Maybe it's better to use another color, maybe blue. Blue like this one. Like this one. But if the slope is the same, like this way, they can identify the same you can have the equivalence class. So for instance, so phi of gamma, so this is gamma 1 and gamma 2 of t at t equals to 0 is equal to d phi gamma 2 t dt at t equals to 0. And that will give you the same tangent vector like this. So therefore, tangent vector can be identified with all the curve from out to segment to M, where the gamma 0 is equal to P, and identify this equivalence class. Here, in this case, gamma 1 and gamma 2 are the equivalent. So you can just identify like this. That's how you. And in local coordinate, so this tangent vector can be just write down. So this local coordinate, 局部坐标。So 这个对吗？ Yeah. So here, if you just write down like this way, so here you can just write down. So the xp can be write down as follows: xi at the local coordinate. Local coordinate. So, in fact, this a basis of can be an basis of TPM. And then xp of I can be written up the like this. So this means what? So xi, so this phi can be understood as a local current, as I mentioned, like this. So at each open patch, you can identify, you can have a coordinate, local coordinate like this way. X1, X2, Xn, okay, like this way. Then you can have a notion. You can have a notion of d xi and I gamma of t. So which measures how this curve is moved along the t is the variable of the segment, t is the variable of the segment. Okay. So the curve is parameterized by t. And if you take a derivative with respect to, then you can just really have a tangent vector like this. Okay, of curve. dt. That is the xp of I, xp of upper. That is really speed of this curve. Speed of this curve. Okay. And the basis is derivative like this. Derivative like this. So those are basics. So the tangent vector basis can be written like a derivative, like it's just notation. Can be, and you understand why it can be written like. And if you have a different open chart, for instance, if you have a different open chart. Suppose you have yellow and blue. Like this way. And the y is mapped to the yellow by x. I call it this one is the x1, so to xn. The other blue is mapped to by y1, yn, like this way. Okay. And then do the coordinate transformation from y to x by the following. It's very simple by just Jacobian matrix. So and then this base transformation is called Jacobian matrix. That's one. So it's just because I mean here again, so you have a function in the overlap region, so you can x can be written in terms of the function of y. So y is up to like this way. So x can be written the function of y. And if you take a derivative, you will get the transition from 1 to here. Okay. Okay, any question at this moment? Okay, so then okay, so if you just now from now on, so we will consider the following thing. So we just consider tangent bundle, tangent space, and then we just glue them together, all over the manifold. That will give you shift tangent bundle. And also, if you have this smoothly just distribute these tangent vector over the manifold, you will get that so-called vector field, 闪电场. So that's what you get. So where should I do it? Okay. So at each point, so we have something like a. So at each point we have point P, and you have tangent space TBM. We have a tangent space, and then you just point Q. You have a tangent space TQM. Okay. At each point you have a tangent space, and you just glue them together. So tangent space, tangent bundle is just P. So, moreover, so in other words, if you have a manifold M with P, you have a tangent space, like this way. And then you just consider point Q, you have another tangent space. And it just you just consider collection of these tangent space. If you just consider collection tangent space, you get the so-called tangent bundle. So that is chip. And at this point, you can have the open patch U is mapped to x1 equal to xn to this point. Okay, like this way. Then, so here you can just have this is just alpha I, delta xi. I just use Einstein convention. So usually I is equal to 1 to n. Just assume. And alpha I is just number. Alpha I is just number. Okay. And then at this point, you just have a so-called trivialization. So and then from here to I, M is just this is P is mapped to. So any point. So you just consider all the tangent bundle. So this itself become manifold. This itself become manifold. This itself become manifold. And which the dimension is what? Dimension of this tangent bundle is what? Huh? Somebody said it broke down. So okay, so tangent bundle, tangent space, the vector space, dimension is what? N dimension. Okay. N dimension. Vector space. Vector space. Okay, and if you look at this, M itself has an n-dimensional manifold. M itself, in addition to each point, you have an n-dimensional vector space. Okay? At each point of M, you have an additional vector space. Okay? Therefore, what's the dimension of the tangent bundle? What's the dimension of tangent bundle? Otherwise, this direction is the n-dimensional. This direction is n-dimensional because fiber is n-dimensional. Tangent space. So therefore, the dimension is what? M-dimensional manifold times n-dimensional manifold. What's the dimension? Huh? Product one has how many dimensions? What?
And total.
N plus N dimension. Think about it. So for instance, S1 plus S1 is what? S1 process torus or 面 is T2. It's just 1 plus 1 is equal to 2-dimensional. It's not 1 times 1. S1 times S1. S1 times S1, you get a 2-dimensional surface. Okay? Then, what is the dimension of the tangent space? Tangent bundle. What is the dimension of tangent bundle? Why this is 2-dimensional? Because 1-dimensional as long as this is one-dimensional, this is one-dimensional, and this is one-dimensional, and we got two-dimensional. So one direction is the M itself, n-dimensional. But a fiber is n-dimensional vector space. In total dimension is what? Good. Tangent bundle itself is 2n-dimensional manifold. 2n-dimensional manifold. Okay. So how do you see the manifold structure? No. So how do you see manifold structure? What is a manifold? Manifold is that you have an open covering. What is open covering? And you have a local coordinate. Yeah. And then transition function. Smooth transition function. Okay. How do you see that? So suppose the original manifold has the touch U. Okay. So this U has an x1 to xn. The local coordinate around here is x1, xn. And also, the tangent space also has a basis. As a derivative, you just write down derivative like this. So those are the basis of the tangent space, tangent bundle. Okay. So here, we suppose you have so that is the part. Okay, and at each point, so this red part can be correspond to like this one. So, I mean, I cannot write down the two-dimensional manifold simultaneously. So, suppose this red part corresponds to this red part, okay, on N. Then, at each point, you have a fiber. And then here you have a basis, del x1, and then del x2, and so on. So the basis over the fiber, tangent space direction is this, and then so this red direction you have the other coordinate x1 and x2 like this. So the total basis is like this. Those are open. Can be understood as open. Okay, and then okay. And suppose another basis, you have the y1 and y2. Yn. Okay. It can be understood as like this way. And then this basis is the this basis y1 and yn, and around this the basis del y1 del y2. along the file. And then it's a transition function. It's just that you just how they glue them together. How they glue them together in this overlap. In this overlap. And the overlap is just a function. Okay, like this. You can just have like this. So this is the transition function from y to x. That's the transition function. Okay. Do you understand what I mean? Do you understand what I mean? So, and this is called local trivialization. If we have a u to the u times Rn, so x1, xn is mapped to x1 total xn times delta. Okay, this is called local trivialization. Local trivialization. So trivialization means that the pi inverse of u. Pi inverse. Pi inverse of u is that the so what I meant is so you have a tangent space, tangent bundle M, and you have a manifold M. Pi is just projection to the M itself. So therefore, so at each point P, you have a tangent space, TPM. Okay? And at any point of TPM is just mapped to point P. Okay? That is a so that is the projection of TM M, like this. So any point here is mapped to here. So now, if you have the open space U, maybe it's better to use red color. Therefore, so if you have open space U, then pi inverse is exactly this place. This place. Pi inverse U is just all the fiber or like a tangent space along U. So in that case, you can just have a product. So this is the object. So this pi inverse of U can be identified with U plus Rn, where Rn is this tangent space direction. And the transition functions, essentially, you just glue them together nicely. Transition function is just glue them together. like this way. So here you just write down everything in the overlapping region here. Overlapping region here, you can just have a transition from y to x or x to y. That is given like this. The base. That's okay. I think it's a good place to stop. Let's take a break. Let's take a break. I'm sorry?
I send you a message on the chat.
Oh, you're a master student? Yeah. Yeah. So for math students, it's too easy.
And first chapter. I deal with some
How do you define hydrogen group? How do you define hydrogen group? So is that like Yes. So RPN is essentially just one, and you just have the opposite one. For example, normal hemisphere and common hemisphere is being identified, except in equators you have to identify. So normal hemisphere, except this equator, is just an open disk. So therefore, open disk is just open disk is RRM. I mean, what does it open disk? Oh, I think this is like this. Yeah, open disk is like this. And then, if you look at the equator, you just identify opposite point, right? Therefore, what's left is this part, red part. And you just identify these 2 points. And the red part and the opposite part is identified. You just identify like this. So this one is also RPN minus 1. So then, if you look at, so except the RPN minus 1 is again the same thing, right? So the RPN is the SN minus 1. And then identify top and bottom. And you have the open disk N minus 1. And then just iterate or the N minus 1, N minus 2. And then you just iterate it. QDM. But at the end, it should be point. It should be point. And the open disk with RP1 is just S1. Because I mean, if RP1 is S1, and you just identify the opposite point, like this way, then at the end of the day, so you get this one, and identify this one and this one, which is just this one. Okay, shall we resume? Okay. So we just consider give you a cheat. And we can consider so-called section. So you have so vector bundle is the Chanliang. So vector bundle. I mean, so we will generalize later. So this is one example of the vector bundle. It's called. So you have a manifold, and then you have a fiber structure. Those are called vector bundle, and which we will learn later. And then tangent bundle is one of the examples. Another example we will learn is cotangent bundle. You chase. All those things, you can always consider the projection from bundle to manifold itself. Okay? Manifold itself. And then consider so-called section. A map section, which is called the P of S of pi is equal to P. That's so what you did is that the section. Section is called 解面. Is it correct? 解面. So at each point P, you assign some section S of P. So at the tangent space, so that each point P, you just assign a point on the tangent space. Then if you apply the pi again, S pi again, you just go back to P. Okay, that's what I mean. So therefore, at each point you just assign it. So just each point you just assign a point S. So you just assign like this. Like this one. So this is called section. And the section of a vector field, tangent bundle is called vector field. So smooth map. Smooth. That's that. So this is called the vector field. So assignment is P to XP is the it's called vector field. So recall that at each point on tangent space is a vector field. Tangent space, tangent vector. So at each point here is just XP, which is like a XPI and delta XI. So at each point P here is that tangent vector. And you just smoothly bury this tangent vector. Okay. So what's really happening is that smoothly balanced. So what's really happening is that at each point, you just assign the tangent vector XP, and you just smoothly vary along the end. So those are called tangent vector. Okay. On the manifold, you just smoothly those are vectors. And then the one, so at the beginning of the lecture, we learned the formula Hopf theorem. So and then I wrote like something like a vector field like this way. So I wrote the vector field like this way, and this is 0 here, and then south pole and north pole have a 0 here. Okay. Those are exactly the one section of the tangent field. And if you look at the here, the point here, okay, point here is just a 0 of the tangent space at the origin of tangent space. Okay. In that case, this point corresponds to 0 of the vector field. At some point around here, it can be something like a very small. So those are the 0 of the vector field. So this point is also 0 of the vector field. Because there is no length there. There is no length. On the other hand, here you have a length here. Those have a length corresponds to these tangents. Okay. 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 And they satisfy. So for instance, if you write down the sphere, okay. So for instance, consider torus. On the torus, you have a this kind of vector field we can consider. Like this kind of vector field. You just rotate like this. So this can be understood as follows. So torus can be just obtained, as I mentioned, just identify the rectangle with identify top and bottom edges and left and right edges. We just identify. And then so you just write down x1, x2 like this way. Like this. So the vector field is literally like a translation of the x1 direction. that is derivative of x1. You just write down like this. That is a vector. X is. Okay. And another vector field one can write down is something like this one. Like this way. Okay. Like this. So if you write down like this way, this is like something like this kind of vector. Okay. So those are examples of the vector here. Another example is just S1. If you consider S1, S1. Okay. Oh, okay, or sphere. It's a boring example. Yeah, I'm not gonna draw everything. So everywhere. So vector field every point has a here. So like this one. Like this one. Okay. Like this one. Then you can just rotate along x3 axis. Okay. If you can rotate along x3 axis, what's going to happen? The vector will look like this. Like this. So how do you write this vector field? How do you write? So first of all, where's the zero of this vector field? Yeah. So it's just rotation along x3 axis. It just give you generate x3 axis. So therefore north pole and south pole are zero. And then if you embed S2 inside R3, okay? So if you embed S2 inside R3, so this vector field y x can be written like this way: minus x1 x2 plus like this. Can you see that? So for instance, if you look at this point, when x2 is equal to 0, so here x2 equals to 0, okay? We just directed to x2, delta x2. So this direction delta x2, right? And here is just the x1, 1, 0, 0. Meaning what I meant is x1, x2, x3. Coordinate, x1 coordinate is 1 right here. If you go to unit sphere, this is x1 coordinate is 1, and then x2 is 0, and x3 is 0. So this is x2. How about here? This is delta x1. So this is 0, 1, 0. 0, 1, 0. And then, actually minus sign, you need a minus sign. Because it's the opposite direction of x1. So therefore, minus delta x1. Okay? So then if you substitute this one, you get that. Do something strange. I think mine's the opposite. Mine's the opposite. Mine's the opposite. So here, if you substitute 1, 0, 0. So here 1 and 0. So then you get the delta x2, right? On the other hand, 0, 1, 0 is the 0 and 1. So therefore you get the negative delta x1. You understand what I mean? So like this way. So this vector field inside R3 can be written like this. You understand what I mean? Is it okay? So this rotational, and then if you go to on top, x1, x2 is 0, 0, 1. If you substitute 0, 0, you get the vector field becomes 0 here. So therefore, okay, so those are the example. And for instance, if you look at the 0 here, there's a 2, 0. And then at the point here, the vector field is something like this way. Okay, this is North Pole. And if you rotate like this, what is the index of this theory? Do you remember index? So you just start with like upper one and just rotate like this way, like in 2 pi. So therefore, this index of North Pole of this y is equal to 1. The same thing happens in South Pole. So therefore, 1 plus y is equal to 2, which is order characteristic of S. Okay. Now let's look at the property of this vector field. So often people just write down this section. This section is something like space of section is something like a T of M. T of M and the gamma of the whole vector field. I just write down this fragment of X. and like this vector field. So this is the space of vector field, all vector field. And if you have the vector field, so at each point, if you look at each point, this is tangent vector. Well, tangent vector is mapped from where to where? Tangent field is mapped from where to where? The infinity of n is a function to R. Okay? You assign function to R, some number. You assign function to number. But if you bury this P, so vector field is just you need to bury this P along the manifold. Okay? So therefore, if you bury P, the number is also buried. Okay? At the end of the day, what you get is that okay? So here, suppose you just assign that xp of f is just number. Given a function f, xp of f is just number. But you just bury this p along this manifold n, then you just number is also buried. Number also buried. So therefore, each point you just assign some number. This will give you a function. Okay? This will give you a function. Manifold to a function of n. Point of the number, and if you change the point p, you get a different number. And at the end of the day, you get the function over there. So therefore, the vector field is C infinity to C infinity. It's smooth. So, given the function, so one is linearity. So x alpha f plus beta g is equal to alpha x of f plus beta x of g. So linearity, and also another thing, Leibniz rule. So x fg is equal to x of f times g plus like this. Okay. So this one is function. X of f is function. X of g is also function over n. Okay. And even if you just add them up, still you have a function over n. That's what we mean. And here, x of f is the function. Function times g is also function. Function times x of g is a function, is function. If you add them up, it's still function. That's what you mean. And what does Leibniz rule means? What does Leibniz rule means? Essentially, this is equivalent to first derivative. First derivative. Okay. For instance, Rn, in Rn, there is a function, whatever function you can call it. R is enough. R is enough. Suppose R is enough. Suppose in R, you can have the vector field is something like that. Vector field is delta x. Okay. And can you give me some function over R? Can you give me one function? Function over R. So the coordinate is x. Can you give me function? So he said x squared, f is x squared. Another function, can you give me another function? Okay, so g is x. Suppose x is second derivative. Suppose x is second derivative. Let's compute the right hand side. Left hand side, sorry, left hand side. So del square, del x square. Okay, let me write down. Left hand side is equal to del square, del x square. F is x square, so the x cubed. Okay, x cubed. And this is equal to 6x. Is it okay? Right hand side. Then this one is equal to x, and this is 0, right? So left hand side is not equal to right hand side. So therefore, second derivative cannot be vector field. So but if you change just like this way, so it can be some vector field, it can be some whatever functions you can add like this. Okay. Then right hand side is like this way. Oh, I shouldn't use f because I already. Let's see alpha of x. Alpha of x left hand side. So this one is equal to 3 times alpha. 3 times alpha of x and x squared. On the other hand, right hand side is the alpha of x, and then here alpha of x. Okay. So then here you will get that alpha of x 2x plus here you get the alpha of x and the x squared. Oh, sorry, x squared. Is it okay? And if you add them up, you get 3 like this. So left hand side equal to right hand side. Okay. So therefore, this is a vector field. So this Leibniz rule literally means that the tangent vector and also the vector field is just the first derivative. Is that what it means? That's what it means. Any question on this one? Okay. So if you look at definition, it's so boring. Okay? If you look at the definition, it's boring, but it has a meaning. So this Leibniz rule is the first derivative, the meaning. And the linearity means that the space of vector field, this space of vector field here is a linear. You can add them up. That's what you mean. So now, okay, so okay. So if the x and y are vector field or manifold, then from the linearity over there, sorry. In fact, sorry, what I mentioned is not correct. Linearity is that how the vector field acts on the combination, like this one. That's how what it follows. And then f is a function of n, then x plus x, y is also the vector field. And also f times x is also vector field. Okay, that's very easy to see. So for instance here, here is just a x1 delta x2, and then this itself can be vector field. This itself can be vector. And this itself can be vector field, but you can add them up. That's also. But you can also add a 2 here, some number here, or maybe some other function you can add. That is also become vector. Okay. On the other hand, if you multiply them, this is not vector field. Because I mean, if you just multiply them, if you act like this way, you just apply each Leibniz rule. So this x so y over f is function. Okay. So therefore you can act like this way. So, according to Leibniz rule, it should satisfy this rule. Okay. However, this does not satisfy this Leibniz rule. xy axle fg should be this times this. This plus this. You don't need these terms. So these are extra terms that doesn't satisfy. That violates Leibniz rule. xy is if it is a vector field. Okay? If you ask fg, xy axle f or xy axle g, these are two terms. Okay? On the other hand, these two terms are extra terms that violate Leibniz rule. Okay? So therefore, xy cannot be vector field. Do you understand what I mean? Is that okay? Because what I did is just that if x and y are vector field, we just apply each one by using Leibniz rule. But at the end, so xy does not satisfy. So therefore, xy cannot be vector. On the other hand, xy minus yx, if you consider such a quantity, I call it this one, it's like this one. This is vector. Because if you swap x and y, and minus, if you take a negative, what you get, so these, if you swap them together, you get exactly this one. If you swap them, you get this one. And if you take a minus sign, they cancel. They cancel. So therefore, if you apply xy as g, then what you get is that the it's satisfied. Because you just swap and take a negative sign, then you get this one. And then from here, you get, and they satisfy Leibniz rule. Okay. Okay. Therefore, this is the vector field. And this is called Lie bracket. So this Lie bracket satisfies the following thing. The bilinear. What does bilinear mean? What does bilinear mean? Can you write down the definition of bilinear? Somebody. Can somebody write the definition of bilinear? Can anybody write the definition of bilinear? Does anybody want to try? Bilinear. Thank you very much. This is last time. So bilinear means, so here x1, x2, then you just have That's what I. So property 1. Property 2 is anti-symmetric. Means that that's super easy because the definition is given here. xy minus yx. So this is very simple. Number 3. Jacobian. Jacobianity. So this is Jacobian. That's a Jacobian. This can be checked by just acting on some function. So just write, oh, yeah. So this can be checked. Okay, so this is the exercise. Show this in this exercise. I mean, it's not that. I mean, you just use this definition and apply a function f. You can see this. Okay. Any question at this moment? So the vector field is 响亮强的这个代数结果。Okay. And another thing we can learn is about it's a flow. So integral curve. Flow of this curve. So for instance, this one. So this one, oh, I already read, sorry. So this is the vector field along S2, and then what is the flow of this? Flow of this one is just rotation along the axis. Do you understand? So therefore, it just acts as a and then do I need to? Sorry. Minus sign must be here. Here? Is it correct? No. Minus 80. No. Sorry, I should have known that. Like this way? I forgot. Second line? Here? And you don't need this one? Yes, that's true. That's true. Okay. That's a rotation. The flow of this flow vector field is really this give you the homomorphism on the manifold. So dimension. So if you have like so another thing is that if you have like this way on the torus, so the flow is the function is equal to T0 like this. Oh, sorry, I think I should mention that this is not precise. T0 on a torus. If it is torus, so this is the x1, x2. Okay, so that's what's going to happen. And for instance, if you have an R2, and if you have like this kind of vector field, which is the x is equal to alpha, beta, then flow f of t should be something like a alpha t, alpha t and beta t. So that's how it works. So if you have a point here, and it just after time t, it just moves to around here like this. It just flow means that just after time t, along the vector field, you just flow to the along the vector field. That's what it means. Along the vector field, you just flow along the vector field, and time t, you just move to this point, and if you move another time s, you get to this point, and so on. That is the flow of the or integral curve of the vector field, single vector. Okay. So the definition of flow is as follows. Flow like this way. So you start with, okay, you have a manifold, and start point P, and then you just there's a vector field, and you just move along this curve. This gamma of T, gamma of T. And then definition is given by gamma of Tp is equal to like this. So dimension tangent vector can be just defined by taking derivative of the curve, right? So taking derivative curve. So you have a gamma of T. So gamma of T means that if you have a P, point P, at the time T, you just flow like this way. You just have a gamma T of P. Okay? Gamma T of P. And then if you take a derivative, then that will give you x gamma T of P at the point. This is a tangent vector along at this point of the vector field. So that's what's really happening. Okay, so that's one. Okay, so that's what's really happening. Any question at this moment? And this one, the flow. Defined on a compact manifold. Compact manifold. So for instance, there's something strange will happen. If you have a point, so you just get rid of some point from manifold, okay? And you have a vector field. You just get rid of point here. Oh, sorry. Okay. I will explain later. So next time. So if you have a point like this way, vector field become like this way. Suppose towards the point which is omitted. Then if you along the flow, if you just go along the flow, you cannot extend because I just get rid of the point. So in that case, you cannot define the flow in R, arbitrary time t. It's some you need to redefine this time region correctly. That will happen for non-compact manifold. Compact means that you just remove like a compact manifold do not have such a point. So let's stop here and then yeah, let's move next time. Did I?